Okay, hello everyone, welcome back to my YouTube channel and welcome to this playlist about power system analysis. Okay, thank you very much for watching my videos. As you must be aware, we have been working with short circuit analysis for a few classes, a few videos, and today I have a numerical example over here. Okay, this is a classical problem. Okay, it's very simple and easy to understand. Okay, what you need to do here is basically check your understanding about symmetrical components. Okay, here we have a synchronous generator and supplies electricity to a synchronous motor using a two-winding power transformer, and this two-winding power transformer is star delta connected. Okay, the generator is connected on the star side of the transformer. Okay, just for illustrating what is the situation, what we have here is basically we have here is a synchronous generator. In this side we have a two winding transformer. Okay, and they are saying that the generator is connected at the star side, and the delta side is for the motor. Okay, we have here a motor. Okay, this is the generator and this is the motor. Okay, and then they say that there is suddenly a fault occurs. Okay, we have a fault and it's at the terminals of the transformer. Okay, we have a fault. We don't know what kind of fault is that one. Okay, it's something that we need to investigate. However, the symmetrical components, I mean, somebody run the calculations here, somebody or somebody gives you some phasor measurements, and we get here the current that is coming here from the motor. Yes, we have positive, negative, and zero sequence, and then we have here the current that is coming from the generator towards the fault. Okay, in this very specific problem there is a very important clue here. This is a very important information. In this case, the subtransient d-axis reactance is equal to the positive and negative sequence. Okay, and that is happening also for both for the motor and the generator. Okay, now there are a few questions over here. Using symmetrical components, describe the type of fault. That is something that we need to understand. Then calculate the pre-fault currents, then calculate the fault, the subtransient fault currents, yeah, and then calculate the subtransient current contribution coming from the generator in per unit. Okay, and this is a very simple problem. Okay, this is a very simple problem. Okay, what we have here is the situation that we have a generator, we have a clear generator here, and we have a motor. There is a fault over there, there is a short circuit over there. We don't know what kind of short circuit, but we need to investigate that. Okay, well, let's start with the solution. Okay, as you can see here, let me start here with the solution. Let me put this a bit up. Okay, the first thing that you must understand is, okay, we have here the representation, yeah, and we have the generator, we have the motor, and there is a fault here, there is a fault here, and there are some current contribution coming from the motor, there are some current contribution coming here from the generator. Okay, this is the subtransient, this is the subtransient contribution. Okay, and here the fault is happening when both currents come over there. Okay, it's equal the generator contribution, subtransient contribution, plus the motor subtransient contribution. Okay, That is what you need to understand over there. However, you must know that this is ABC, okay? Okay. Now the first step. Well, the first step that you need to understand is extremely simple, okay? The first thing that you must understand is we need to understand that the current's contributions, they are going to the fault point, okay? And those fault contributions, they are going to the fault point, and what you need to know is that at each sequence network, the contribution sum, and both of them, they are going out, okay? Let me go here, okay? Let me come back here a bit. This is the circuit, this is the situation. Yes, they are a generator, but we have here it's one, yes. We have the transformer, yes. Then here we have the fault point P, and then here we have the motor, but remember the motor have the same okay. This is the positive sequence network, okay? As you can see over here, there are some voltage sources, internal voltages, and here we have the model. This is the transformer, this is the generator, okay? And we can say this is the positive sequence, okay? If there is a contribution over here, we can say that this is, for a moment, I will not include the subtransient symbol because it will be simple for you, and don't overcomplicate the notation. This is the positive sequence contribution coming from the generator. This is the positive sequence contribution coming from the motor. When both of them, they arrive to this node, this is the positive sequence current going to the fault, okay? And it's coming back here, okay? This network also have a negative sequence. Let me put over here. All of you must remember the negative sequence. This is the reactance. This is the transformer, okay? This is the point P. We have here the negative sequence reactance, okay? And here we have this is the positive sequence. And here is the negative sequence equivalent network, okay? This is the network. And this is the negative sequence network, okay? During the fault condition, this is the negative sequence contribution coming from the motor, and during the negative sequence, during the fault, this is the negative sequence coming from the generator, okay? Both of them, they sum here, and the current that is going out is the negative sequence current, okay? Then we can describe what is the negative sequence model, the zero sequence model, okay? The zero sequence model, we have here the generator, we have here the transformer, okay? This is, let me put in this way, this is the H0 from the generator, yes? And in this case, we are assuming this one is the transformer zero sequence, okay? And we have a star delta connected here, okay? Here is the point P, but because we have here at delta connection, we have an open circuit here, and this will be the zero sequence current, okay? And this will be the zero sequence reactant from the motor, okay? And this is again the zero sequence network. Okay, what I'm trying to say is right now we have the three different sequence networks, okay? Positive, negative, and zero. But in all of them, what you need to understand is that the positive sequence, for instance, is the sum of this one, In the negative sequence, it's happening the same. Contribution, negative sequence contribution coming from the generator, negative sequence contribution coming from the motor, and it's the same for the zero sequence. We have here the zero sequence component coming from the generator plus the zero sequence component coming from the motor. Okay. Explanation simple. You can see here the sequence networks, and the quite interesting thing is this one is 0, you can see, and here we have some value. Okay. Well, this is the graphical representation. You can see from there it's where it's coming those equations that we have here. Okay. For the positive sequence, we have the contribution coming from the motor, from the generator. From the negative sequence, we have contribution coming from the motor and generator, and similar approach is used for the zero sequence. Okay, from the zero sequence, we have contribution from the motor and generator. One of them is 0 coming from the data. And what is the interesting thing here? As you can see, the fault, the positive sequence current going to the fault is minus 3J per unit. The negative is the same value, minus 3J, and the zero sequence is minus 3J. Okay? As you must be aware, the reader, I mean my understanding, my students or anyone watching my videos, you must recognize that the connection, the only connection that allows you to have a positive, negative, and zero sequence with the same value is the single line ground fault. Okay, what I'm telling you is that the numerical results that we got from calculating the positive, negative, and zero sequence, those numerical results allow me to conclude that this short circuit represents a single line ground fault, because you can see that the positive, negative, and zero sequence, all of them, they have the same value. Okay. What I will do now is I will show you, this is basically, let me put here, okay. What I am showing now is the interconnection. Remember, this is the positive sequence, this is the positive sequence, this is the negative sequence, and this is the zero sequence. Okay. As you can see over there, they are positive sequence, negative sequence, zero sequence, and all of them are interconnected in series, because this is a single line to ground fault. Okay. Okay, and here what you can see, this is the positive sequence contribution coming from the generator, this is the negative sequence contribution coming from the generator, and there is not a zero sequence contribution coming from the generator. Okay. Okay, it's very simple. It's something that all my students, they can do straight away. Okay. What is the next question in this problem? Okay, the next question in this problem is something that is quite interesting. Okay, I can see over here. The question is, what is the pre-fault current? Okay, what is the pre-fault current that is going to the motor? Okay, this is something very simple. Okay, here we have positive sequence, negative sequence, and zero sequence. Okay. But at this time, what we are interested to know, what we want to know is what is the current that is going to the motor at pre-fault conditions. Okay, many of my students, they were very confused, and that is the reason that now I need to explain. Okay, what I want that you understand is that for this very specific circuit, for this very specific power system, where the positive and negative sequence are equal, again, this is a property, a circuit property. in this very specific circuit, positive and negative sequence, they have the same value, okay? And that condition is key to understand this equation over here, okay? What I need that you understand is that the current that is a phase A current, this is the phase A current, or the line A current coming from the generator, is the difference between the positive and negative sequence. Okay? It's the difference between the positive and negative sequence contribution. That is what my student must demonstrate. And also, as you can see over here, the line A, the current in pre-fault condition is equal to the positive minus the negative sequence contribution with a negative sign, okay? As we are expecting, if there is no fault in the system, the current that is coming from the generator to the motor must be equal to the current going from the motor to the generator multiplied by -1. And that is what is happening here. I believe if you look the numerical results, if you only care about the numerical results, probably you can see that those numbers are similar, okay? This is a minus here. There is a minus over there. Because the current coming from the motor to the generator is minus the current coming from the on the line A coming from the generator to the motor. Okay? Well, now it's time to use some white paper and use my ugly handwriting. I am sorry, but I don't have right now time to do a very elegant and well-prepared document. I'm afraid that this is a very busy time. However, what I want to tell you is the following. Okay, in this question, what we want to know is the pre-fault current. Okay, what is the pre-fault conditions? The pre-fault condition. Okay. This is the model coming from the generator. This is the model of the generator. Okay. This is the reactance of the transformer. This is the reactance of the motor. And we have here, the internal voltage of the motor, and this is the internal voltage of the generator. Here, remember, in this case, what we need to know that is there is a current here, okay, and this is pre-fault condition. If this system is if this system is working properly, this is the positive sequence, okay, and as you can see over here, this should be the positive sequence of this motor. This should be the the generator. This should be the positive sequence of the motor, and this is the reactance of the transformer. Okay. In pre-fault conditions, also we can have negative sequence model. And also we can have zero sequence, okay? But if we assume that this system is symmetrical and balanced previous to the fault, the current I in line A should be AG okay, and because these ones are the same, okay, what is the problem? We want this current, but the issue is We don't know those internal voltages. We don't have any idea. We don't know what is the positive sequence value of the reactance. We don't know the transformer reactance. To be honest, this equation is useless. It's useless as this equation alone, okay? But what we need to understand is the following. We want to know this current. This is the pre-fault current, okay? This is the pre-fault current, okay? And this is what we want. Now, what are our options? I will call this equation number 1, okay? Okay. Now, this is the pre-fault conditions. But the only place that I have very good data is during the fault conditions. During the fault conditions, I know the symmetrical components of all currents, okay? What I will do now is I will do the following, okay? Let me go back now and let me see the fault conditions, okay? Fault conditions. During fault conditions, we have here the positive sequence, the transformer, and we have the positive sequence coming from the motor, yes? Okay? But during fault condition, the current here is known. This current contribution over here is known. And also this one, this current contribution coming from the motor is also known. Okay? We don't know those 3 values and those 2 more 5 values that we don't know. This is the positive sequence network. Okay? What's about the negative sequence? Okay? In the negative sequence, we have here the negative sequence. We have the transformer here. And now what we have here is, this is the negative sequence contribution coming from the motor. This is the negative sequence contribution coming from the generator. Sorry, this is the generator. When they zoom over here, this is the negative sequence current, okay? However, what is the interesting thing? Where this is a single line to ground fault. And what is happening is that the positive sequence, the negative sequence, and the zero sequence, all of them are the same. That is the first clue that is very important in this problem. Another clue that is extremely important is that the motor and the generator, all of them, they have positive and negative sequence, and both of them are equal, okay? What I will do now is just play with circuit analysis. Very basic circuit analysis, okay? That is what I will do now. What I will do now is let me write the following, okay? Let me write equations over here. And the first equation that I want to do is the following, okay? The first equation that I want to do is the following. I believe you can see that here, this size of the circuit has the same terminal voltage here that this size of the circuit. For that reason, what I will do is just basically use Kirchhoff voltage law, okay? Okay, now what I'm showing here is the, we already identified that this is a line to ground fault, okay? And because it's a line to ground fault, we are interconnecting the 3 sequence networks in series, okay? You can see here, this is the positive sequence network, negative sequence network, and here we have the zero sequence network, okay? What is interesting here is that the contribution coming from the motor, from the generator and the motor, both of them going to the fault point, and from there we have the positive sequence, okay? It's the same happening here. We have a negative sequence contribution coming from the generator, negative sequence contribution coming from the motor. both of them add up and going out, and this is the negative sequence current, okay? However, because we have a single line to ground, this is the important condition here, okay? Because we have a single line to ground fault, well, the condition is that the positive sequence equal to the negative sequence equal to the zero sequence, okay? And that is what is happening here, okay? We already demonstrate that, okay? Now, what is the job now? Well, the job now is that I want to know the pre-fault conditions, but we don't know the positive sequence, we don't know the transformer, we don't know the internal voltages. There is something that we know here, that is that the subtransient voltage is equal to the steady state. And we know that because we know that those machines will not change so fast, okay? During the fault conditions, the voltages will not change so fast during the fault conditions, okay? And now what you can see over here, is the interconnection of those networks, okay? Now it's time to do some equations, okay? Let me start to write few equations over here, okay? The first thing that I will do is, let's start writing the Kirchhoff voltage law equation, okay, for the positive sequence, the Kirchhoff voltage law equation here. As you can see over there, we can say that AG is equal to minus plus, okay. I believe you can see that I can reorganize this equation like okay. And then we have another more term, and let's call this the equation number 2, okay? This is in the positive sequence, okay? Now let's do something similar for the negative sequence, okay? For the negative sequence, okay, for the negative sequence, we can say here okay, and let me reorganize this equation. We can write this equation like and this is equation number 3, okay? What I will do now is let me put together equation 2 and equation 3, okay? We can put together, let me remove this one from the back. And now what we can do is and the second equation is okay. we have right now both equations over there. Something that I would like to do is the following, okay? First, you must remember that the positive and negative sequence, they are equal in this very specific problem, okay? And what I want to do is multiply this equation by -1 and then sum to the other equation, okay? What I will do is this. Now x1 is common factor, okay? Common factor, and we can say that that is okay, but also is common factor to and then we have okay. Now the situation is very simple. Why? Because if you remember from equation number 1, we can say that the current as a consequence, we can rewrite this equation like and finally this is equation number 4. And what I will do is include equation number 4 in this equation above. Okay. Now the interesting question is the following. Okay. I believe you can see here we can rewrite this like okay, and that is equal to 3 different terms that we have here. The first term is this one. The second term is this one. And the third term is equal to now, what are the conclusions here? Well, this equation is the core of the final conclusion here, okay? This equation over here is the most important equation at the moment, okay? Because what I will do is the following. In order that this term must be equal to this term, one situation that must happen is and as consequence, if this is happening, you can see that this term is equal to this term, and this term is equal to this term, and then also what must happen here is that the equation must satisfy okay, and finally you can rewrite those equations What is the conclusion? For this very specific example, when positive and negative sequence are equal, we can derive the equations, and we can derive the equations that they are combining. If you remember, this is the pre-fault current, and over here in this side we have the symmetrical components. We have the symmetrical components. During the fault condition, okay? Well, I hope all my students, they can follow these steps, and they can be sure that the equation that I presented in the previous slides are properly correct, and I hope they can enjoy this very specific deduction, okay? Now let's go back again and continue solving the problem. Now that is clear for all of you, you must remember that I spent a few minutes explaining those equations over here, okay? What I did in the previous white paper with my ugly handwriting was showing to you that those equations over there, they are real, they are properly done, and if the system is having a single ground to fault, and you know the symmetrical components, but also the positive and negative sequence of those elements are the same, well, you can calculate the pre-fault current like the difference between the positive and negative sequence, okay? Well, now that is clear the point, now that is totally clear the point, what we will do is, okay, let's calculate the single phase short circuit current. And to be honest, calculating the single phase short circuit current is something extremely simple, okay? Because you must remember that for a single fault current, the fault current is 3 times the positive sequence current, okay? And in the previous slides, we calculate that positive sequence current based on the data that was provided to you. You must remember that the positive sequence was equal to here you can see the positive sequence is equal to 3J per unit, and what we are doing here is multiplying 3 times the positive current, that is equal to 9 per unit, okay? Minus 9J per unit, okay? What is the next step? Okay, the next step and the final step in the solution of this problem is extremely simple, okay? The final step is that we want to know the specific components of the current that is going from the generator to the transformer, okay? And in this case, what we need to recognize is that the fault is happening on the delta side of this 2-winding transformer, okay? The fault is happening here, and we know the symmetrical components in this side of the generator, and what we need to do is move those symmetrical components to the other side, okay? But because this is a star to the transformer, they are a 30-degree phase angle change. If you look over here, now what I will show you is the basic solution, okay? Okay, what is happening? Well, we have here the generator, we have here the transformer, we have here the motor, okay? This is the motor, this is the generator, this is the star connection, this is the delta connection, the fault happened here, okay? This is the fault. Right now, after our investigation, we know that this is a single line to ground situation, and what we know is the components here, but we want to know is the component on the other side of the transformer at the generator side, okay? Well, as you must remember, when we are moving and there is a transformer that is delta star connection, they are a 30-degree shift on the phase angle, okay? What we are doing here is something very simple, okay? We know that the positive sequence current here, you must remember, is the positive sequence current coming from the generator is equal to plus 8 and minus 4J, okay? It's 0.4J, 0.4J, okay? And that is in the delta side. When we are moving from the delta side to the star side, they are 30-degree, and that is what we are doing here, okay? What we are doing here is rotating 30-degree the current that we know, and now with the 30-degree, that is the current. This is the current that you can find here. This is the current on the other side, on the star connected side of the generator, okay? And what is the final step? The final step is doing something similar, but now we need to move from one side to the other side the negative component of the generator, okay? What we are doing right now is moving the negative sequence component from the generator from this side to this side. What is the main difference with the previous calculation? Well, the main difference with the previous calculation is instead of using 30-degree positive, because the sequence changed and now is a negative sequence, instead of using positive 30-degree, we need to use negative 30-degree, okay? And when we put the number together, we are moving from one side, and this is the negative sequence. This is the negative sequence current here on the star connected side of the transformer. Now, what we need to do is something very simple. They are not zero sequence current moving through the generator because there is a delta here, and the transformer is, and the fault is on the other side of the delta connection. As a consequence, because the fault is on the low voltage side, and there is a delta connection, there is no circulation of zero sequence component on this side of the transformer, and this is the last part that we need to do, okay? The last part that we need to do is, well, you must remember to calculate A, B, C components. You need to use the matrix A and the vector representing the component 0, 1, 2, okay? And that is what we are doing here. You must remember this is the zero component coming from the generator. This is the positive sequence coming from the generator, and this is the negative sequence coming from the generator, okay? And when we use this property, we obtain here what is the proper current that is coming from the generator at the star side of that transformer. And that includes already the 30-degree shift when you are having a star delta connection, okay? Well, I hope you enjoyed this very basic example. It's a very basic example, but to be honest, there are many things to reflect over there, okay? I believe you can see that in this example, probably the most simple question that was this one require a lot of reflecting about what is happening in the system, okay? I highly suggest that you reflect what is happening with the impedances, positive, negative, and zero sequence inside your system, because those properties will allow you to take very good conclusions, okay? Also, if you are studying and taking my classes of power system protection, having a full understanding of those symmetrical components will help you a lot in the future for the case of these overcurrent protections, okay? Well, it's been a pleasure having all of you over here. I hope you enjoyed this video and you find very useful this video. Okay, thank you very much. Bye now.